Namaste friends, welcome to the second part of the number system series. In the last lesson, we talked about the meaning of the decimal number system and base of a number. In this lesson, we will continue the topic and learn about the binary number system. Electronic devices, especially computers, internally use electricity for computation. These components work in either of the two states, high or low voltage, on or off, presence or absence of current, 1 or 0. Think about your light switch. It can only be in the on or off state, right? We represent these states using the binary number system. Bi means 2. We usually give inputs and get outputs from a computer in the decimal number system. Binary is used internally. It is very important in understanding computer science and computer programming. So, what is binary? Let's look at the unique digits in the binary number system. Well, surprise, surprise, there are only two digits, 0 and 1. Wait, that's all? Yes, that's all. You can represent all possible numbers in binary, just like it is possible in decimal. However, you will need more number of digits, that is bits, to represent a number in binary when compared to decimal. Just like in the decimal number system, we call the individual numbers as digits. In the binary number system, we will call the individual numbers as bit. Bit is the short form for binary digit. There are only two possible bits. They are 0 and 1. Now, let's count in decimal. Repeat after me in your mind. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Notice that you could represent 0 to 9 using one digit only. What next? What if you want to represent a number greater than 9? What do? You add one more digit. 10, 11, 12, 13, and it goes on until 99. Now, let's count in binary. 0, 1. Hmm, what next, huh? You said that there are only two possible bits, 0 and 1. Well, just like in the decimal number system, we added one more digit after 9. In the binary number system, we add one more digit after 1. So, after 0 and 1, the next number in the series is 10. Notice how we read it as 10 and not 10 because we are counting in the binary number system. After 10 we have 11, and after 11 we have 100, and so on. Notice 10 to the base 2 is equal to 2 to the base 10. So we can say 10 in binary is equal to 2 in decimal. 11 to the base 2 is equal to 3 to the base 10. That is 11 in binary is equal to 3 in decimal. 100 to the base 2 is equal to 4 to the base 10. That is 100 in binary is equal to 4 in decimal. Notice to represent the same quantity 4, we need one digit in decimal, whereas 3 digits in binary. Also remember 10 to the base 2 is not equal to 10 to the base 10. Let us quickly look at a conversion table. Remember that you don't need to memorize this table. This is just for your understanding. Notice that 0 in decimal is 0 in binary, so on and so forth. Notice the number 15 in decimal is 1111 in binary. The number 31 in decimal is 11111 in binary. Observe the table carefully and notice that in the binary column we only have zeros and ones. Now, let us try to understand this conversion table a little bit. Notice that 0 and 1 are the same in both decimal and binary. In binary, after the number 1, since we do not have any higher digit, we start using 2 bits to represent the next higher number. So 2 in decimal becomes 10 in binary. Notice that at powers of 2, the number of bits increase by 1. Here, 2 to the power 1 is equal to 2. Similarly, observe the number 4 in decimal, which is equal to 100 in binary. Notice that to represent 3, we needed 2 bits, whereas to represent 4, we needed 3 bits. The number of bits increase by 1 at every increasing power of 2. So 2 to the power 2 is 4. Again, when we go to 8, the number of bits increase from 3 to 4. Here, 2 to the power 3 is 8. Let's say I gave you a box. You can only write a single bit in this box. How many different possible numbers can you write in this box? 2, right? You can have 2 different ways of filling up this box, 0 or 1. Remember, we are dealing with binary numbers here. Now let's say I gave you 2 boxes. You can only write a 1-bit number in each of these boxes. How many different possible numbers can you represent using these boxes? 4, right? You can have 4 different ways of filling up these boxes. 0 to 1, 1. That is 0, 0, 0, 1, 1, 0, and 1, 1. Can you think of any other combination using zeros and ones? No, it's not possible, right? These are the only 4 possible combinations. Now let's generalize this concept for n boxes. How many different possible binary numbers can you represent using n boxes? We saw that with one box we can have 2 combinations, that is 2 to the power 1. With 2 boxes we can have 4 combinations, that is 2 to the power 2. So on until we have n boxes using which we can represent 2 to the power n combinations. That is, with n boxes, you can represent exactly 2 to the power n different types of information. Now let's generalize the same concept for any base b and for any number of boxes n. In the last lesson, we saw for decimal numbers, that is base 10, using n boxes, we can represent 10 to the power n different types of information. In the previous slide, we saw for binary numbers, that is base 2, using n boxes, we can represent 2 to the power n different types of information. So, for a number system with a base b, using n boxes, we can represent b to the power n different types of information. So, 2 to the power 0 is 1. That is, with no boxes, we can represent exactly one piece of information, which is 0. Thank you friends for watching this video. I hope you enjoyed it. Please leave your comments in the section below. See you in the next lesson.